And sit down.
And
Welcome. And welcome everyone to the Quantum Machine Learning Seminar this week. Today we have a flashy, high-end, fancy invited speaker, namely Casper Gyurik from Leiden, who will tell us about like this super cool paper on things that he would say, but like it's very nice, I can say. Casper will still be around for another 2 hours, maybe after the end of the talk, so maybe there's chance to pick up with him. But otherwise, Casper is a very friendly guy. You can attack him over email, and he will also be happy. Would you have questions along the way?
Along the way, yes.
Okay.
That's
Okay. Then we have a soft deadline of 1 hour and a hard deadline of 1.5 hours.
But I think I'll stand here because then I can click my slides. I don't think I should click right.
you want to present them?
Sorry?
Do you want to click them?
Is it if it I'm fine with Fiverr. Oh, that's sick. Okay, let's do it. I don't need to go there. No.
Move forward.
Like ostriches and kangaroos.
Okay, let's try this. Okay. So hi everybody, welcome. This is my talk about exponential separations between classical and quantum learners. Thanks for having me. So I work at University Leiden, so I always have to quote one of the physicists there, and I can do this here in his native language. And the idea behind this talk is, what is der Witz? What's the point? What makes this stuff all work? How do they get it? How do they build it? And what do they actually do? That's sort of what we're trying. Next slide, there you go. So the motivation of this sort of talk, of this research, is understanding the following question, and we just to start that question off, we ask the question: when does quantum beat classical computing? And then I want to put the emphasis on computation. And there's two people you could ask. If you could ask Peter Shor, he would say number theory, cryptanalysis, all this beautiful Shor's algorithm stuff. And if you could ask Feynman, he would probably say studying physics, nature's quantum, damn it. But what if you slightly change the question and remove computation and go to machine learning? You could ask Shor again, whether or not quantum computation beats classical computation for cryptanalysis problems, for these discrete logarithms, for these number theory problems. Hi. And you could ask Feynman the same question. And the answer is, oh, this is back actually. I went back now. I don't know why.
Yeah, it depends on which side of the screen.
Why did I go forward and yeah, it just doesn't work as well as I
New slide.
I'll just go here. Okay. So you could rephrase the question, and if we ask Shor, then he can actually give a positive answer, because there's a plethora of learning separations that are based on cryptography. You could hear some references. However, if you ask Feynman the same questions, it's actually an unknown. I don't have a Ouija board, so I cannot ask him myself. But sort of the idea of this stuff, of the research is, okay, so we have learning separations in cryptanalysis. What makes them work? And can we translate this now to learning separations where we try to understand physical properties? So do we need machine learning to predict physical properties because nature is physical? Yeah. And in quantum machine learning, there's always a distinction between, is my data quantum state or is my data classical? And throughout this talk, my data will be classical. So they're all just measurements from my quantum system, so classical information which exhibits quantum correlations, let's say. So no quantum states, no quantum info, just classical data, but coming from some quantum process. And the main question is, when do complexity theoretical separations imply various kinds of learning separations? So basically, what is the difference between complexity theoretical separations and learning separations? Like, how do we get one from the other? In this sense, how do we get learning separations from complexity theoretical separations? How does that go? How do you get there? And to do so, we first have to understand what a learning separation is and how it has been achieved in the past. So let's define a learning separation. And it's not a machine learning talks without pictures of cats or dogs, and I'm more a dog person. So this is a supervised learning problem. It's a problem of a chihuahua or muffin. You're getting a bunch of labeled examples, which is what makes this problem supervised. So there's data, as they give you some examples of a picture and a label. So a picture of a chihuahua, it's actually a chihuahua, and a muffin, and a muffin. And there's some learning happening, which basically goes through all these examples, and it spits out H, some so-called hypothesis. Just like on most new pictures, it will assign the correct labeling again. How does this look without pictures? This looks in formulas, it looks as follows. At least for my setting, we have concept classes, which I now split up as sort of going over different instance sizes. So you should think about the N here, the N there.
Oh, old school.
The N there as being instance size. So was I still really? Oh, that's funny. I thought it was like a special market. That's why I could try it. Okay.
Maybe this is a special stick.
Who knows? As being instance sizes, so it sort of scales with the size of the domain. So you could think about Ci, which is a function in Cn, going from n bit strings to some label space. And we're going to study sort of behavior as a function of n. Yes.
So this is something that I do sometimes. So C is a sequence of sets. Every Cn is already like a problem defined as a set.
Yes. Yeah. So it's C is a set of sets, or it's a union of sets, and then sort of for every instance size there is a set. So you could define for any size of an integer, there is an associated complexity.
And then for every instance size, is that like a place where you could define problems, or do you already is there already one learning task associated to Cn at the current stage of notation?
Well, in the end, you're going to make statements about the sort of the runtime scaling, sort of the asymptotics. So you need a family for this. If you want to say, so if you want to study scaling as a function of n, you need for every n something to be defined. So if you want, and the goal here is to get asymptotics.
Yes.
Of course, it might also make sense for constant sizes and studying behavior in that regard, but we need to get to asymptotics, so we need for every n something to be defined.
Perfect.
Yes.
So this input size, so it's just like how large are the images?
Exactly.
Okay.
Yes. Yeah. But you could imagine that also. Yeah, the images are still either up to 4K resolution, I guess currently, but it's really a sort of scaling family.
Okay. Good.
But yes, you think about them as resolution images.
And it is just the definition of computational problem in some form. Right?
Exactly. Yes. This is also how I would define a language in complexity. Correct. But now you do this for learning theory. So we have a concept class. This is the thing we're trying to learn. This is going to define our learning problem. And I'll explain later what I mean by trying to learn. But the second component of the learning problem is an input distribution. So in my definition, the input distribution is part of the learning problems. In certain definitions, you should learn a concept class under all distributions. For me, I specify one distribution under which you want to learn this. That's sort of the framework we tackle in this paper. And it's nothing more than sort of the distribution under which you are given your data. And also the distribution under which you should reproduce the function later on. And it's a distribution over inputs. And then to solve a learning problem, you define a learner, which is also two components, which is the function class, the hypothesis class, which is basically the function you will try to approximate your concept with, same domain, same codomain. But there's also a learning algorithm, something which sifts through the data and finds you the right hypothesis to use later on. But as I said, in machine learning, you also have data, which is modeled using the example oracle. It's a black box function, which it's a black box oracle, sort of a machine that if you push a button, you get one example. And the example is drawn according to the distribution, which sort of specified the learning problem earlier on. And now that everything is in place, it's time for the biggest definition I have on my slide, which is PUC. You've probably seen it multiple times, especially in this group. Let's repeat it one more time. We say that a learning problem, which is a concept class together with a distribution. So this is not a for all distribution statement, this is for a specific distribution. We call it sufficiently learnable if there exists a family of hypothesis functions and a learning algorithm, such that if the learning algorithm is given access to a precision parameter epsilon, a precision parameter epsilon, a confidence parameter delta, and the example oracle, so it is given access to the subroutine, it spits out an hypothesis that with probability at least 1 minus delta is close to the concept hidden in the example oracle. So from the example oracle, which has like a C hidden inside of it, you want to find an H which is close to C. and you want it to be epsilon delta close, let's say, probably approximately. These are epsilon and delta. And what is sort of different from the standard, let's say, from the vanilla POC learning framework, is that vanilla POC only studies the sample complexity. Like how many times do I have to push the button of the oracle to find out which C is hidden inside of it? But now, additionally, I also constrain the learner to have a runtime polynomial in N, which is strictly stronger because the oracle is unit cost, and if I only have polynomial time, then I can only press the button polynomial many times anyway. So it's like both sample efficient and also time efficient. And that's the additional constraint we have in efficient POC learning. Studied in the 94s. I don't know, 1990, I think, was the first definition of this. Okay, yes.
Do you assume that in principle one would know C of X, or is C of X hidden for the learner?
It knows the concept class, which is all the C's, but when it's given the oracle, it doesn't know which C. The only thing it knows about C is this example oracle, which you can press and you get one evaluation of it. Okay. If you don't know which function, you know the evaluation. You know it's one of the functions in your problem specification, but there could be exponentially many of them.
So you always also have a sampling. Like you don't just have computational complexity, but also.
Yes, because the sample costs unit time. Yeah. So you only have time to press it polynomial many times anyway if you're constraining your learning algorithm. Yes.
So here when you say that it works with probability at this 1 minus delta, here this refers to the probability with respect to...
With respect to, so the example oracle is a randomized thing. So you might get very uninformative examples. You might get the same 500 times. It happens with very small probability, but it might happen. So it is both with respect to the example oracle and with the internal randomization of the learning algorithm A, which you could also randomize.
So the way I think of it, like delta is the probability that's like outside of your learning, like the probability before the learning, and the one that you have written specifically PRX from the end.
Yeah,
This is like an accuracy. Okay.
Epsilon is an accuracy,
Yes.
and the delta is a failure probability.
Yes.
So the A in POC stands for approximate, that's the delta. The P in POC stands for probably, that's the, sorry, I'm saying it completely wrong. The A stands for approximate, which is epsilon, and the P stands for probable, which is delta. So it might just completely fail, right?
But if it fails, this is due to the fact that this example oracle is fit out a set of
for instance.
samples that are found bad.
Yeah, exactly. That's one way to do it. You could also do the internal randomization of your algorithm, but it's both over A and over the example. And epsilon is like on what fraction of possible inputs are you correct? So it's like the approximate case. Okay, so what is a learning separation? Informally, which is a concept class with distribution that is efficiently learned by a quantum learner to be specified later on, but you cannot efficiently learn it using a classical learner, which doesn't need to be specified later on. So when you see this, you might ask yourself the question, what's so different about this from complexity theory? For instance, you could ask yourself the question, consider concepts like this. They're just parameterized circuits followed on a certain input state, and then you measure it, which is sort of hidden in the circuit now. And suppose you believe the circuit is universal enough such that these functions are classically intractable. You can evaluate them on a classical point computer.
Are you missing an observable? The thing is straight one.
I am missing an observable, yes. I should have put an observable there, yes. And yes, correct.
Elias doesn't believe it's classically intractable.
I'll treat it.
No, let's put a Z somewhere, Z1, and then we're happy.
Yes.
So Z in the first qubit, I'm missing this. I suppose you believe your circuit is universal enough such that this is classically intractable, but quantum you can of course evaluate it. Like, why is this not a learning separation already? So why is sort of saying your concepts are hard, why is that not enough for a learning separation? And if so, why is this sort of satisfactory as a notion of learning? Because it really looks like computation now. Like we just say, concept hard to compute, so learning separation. Like it's, well, why is learning? Like it's only hard to compute, that's what sort of you start from. Well, it's actually kind of different, learning compared to complexity theory. And there's 3 reasons for this. And one of the more important ones is the data gap. In machine learning, you're given data. And data is actually quite powerful resource. When you get data, certain stuff all of a sudden becomes efficiently evaluatable where it was not a priori. I'll give you an example later on. Moreover, you must still ensure quantum learnability. Even though your concepts are efficiently evaluatable, they might not be learnable. And the examples perhaps from this group is that the shallow circuits are not even learnable. Clearly you can evaluate them, clearly you can sample from their distributions, but they're not learnable. You cannot sort of spit out which circuit is generating the examples. Like clearly you can evaluate the function, it's a shallow quantum circuit, but you cannot learn it. So it's also something that you must take care of. Moreover, machine learning typically deals with worst case complexity, like worst case runtime, and in machine learning, you have this epsilon, right? You have the epsilon and PAC, and which is not the worst case because you might fail on the worst case but be correct in this epsilon function, which is a worst case versus heuristic distinction.
A quick comment on the shallowness. It's only like provable non-learnability is only when it's super logarithm. So technically, then also sampling is not efficient.
It's I mean classically not efficient.
No, like you refer to our average case,
Yeah.
blah, 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 right? And then the shallow regime is the like where it's hard, where you can prove hardness is it's super logarithmic then. Like
The quantum computer can still do this, right?
they can efficiently sample.
That's the point.
Okay, you mean that's the way.
Quantum you can evaluate, but quantum you can learn it.
Okay, so
That's yes. So it is indeed clearly not classically evaluate the sample will know what I meant. Quantum, you could of course evaluate the functions, but learning is a difficult part. So that's yes. Yeah, super logarithmic is still fun. Yeah. For quantum. That's yeah. Yes.
Will you also say something about average case complexities?
A bit, yes. Why it sort of works, why the examples we have work. Yes, that's one of the things I'll touch upon as well.
Maybe just to understand, maybe you will talk about this, just on an intuitive level. The first point is this about the fact that, okay, you said the evaluation of C might be hard.
Yes.
But in the problem that we're describing here, you're just given the evaluation. So you are not asked to evaluate it yourself. Is that
You are asked to evaluate it later on in certain regimes, but you're asked to evaluate it when you also already know some evaluations of it.
exactly like in the training data, you're given the evaluations for certain
For
inputs.
certain input,
Yeah,
and you have to extrapolate.
Exactly. Yeah.
Okay.
That's the point, kind of.
Yes, and extrapolation might be easier than just flat out
Sure.
computing.
Yeah.
That's basically the point of this. Which indeed, we go back on this function and yes, I have an observable. I did it. Okay. And let's suppose it's Z1. And let's suppose the part encoded by this phi is somewhat universal. You can sort of generate any circuit that you want in a PQP type sense. And we put in one gate that is parameterized by this theta, and we want to consider these as possible concepts for learning separation. And we want to talk about the data there. Since we assume that this sort of phi makes this function universal for quantum, clearly when a classical algorithm is given phi, it won't be able to evaluate this function f sub phi on points theta unless BPP equals BQP, given the universality of this thing. So you might think, well, this might be a good candidate for learning separation. However, there is a nice explicit form of this function. It is this simple cosine, which means that even though the function from just given phi is hard to evaluate, if I'm given both phi and 3 evaluations of it, I can fit the function through it and I can all of a sudden evaluate the function. So having sort of examples, having access to the data, all of a sudden makes this function tractable. Where a priori, no way you could do it unless BPP equals BQP. If I'm giving 3 evaluations already, so if my problem is both, I'm giving input plus 3 evaluations, then I can fit the cosine and evaluate it with arbitrary theta later on. And also solve, let's say, the hard instances thereof. So this is a clear example of the data gap. Function might be hard, but function plus data is easy. And that's sort of what you need for learning separation, because function plus data needs to be hard. Otherwise, you cannot show that the classical learner cannot do it. However, we do still have a few heroic examples which sort of make all these 3 things go away. And let's analyze how they do it. So we just talked about the data gap. And there's actually a way to get around the data gap. One that people have done, and it worked, and they're doing it again, and it worked, is that you can ensure that the data is efficiently generatable. Why does this work? Well, it gives rise to the magical formula of proving learning separations. Namely that if you have an efficient learner, and you know that you can efficiently generate data, then this implies an efficient non-learning algorithm. Because the non-learning algorithm can just efficiently generate the data, run the learner on it, and then you have a non-learning algorithm. Like that, the data itself doesn't give you extra power because the non-learning algorithm can do it itself. So if that's sort of now the assumption that there cannot exist a non-learning algorithm, that the functions themselves are simply just hard, is already sufficient to deduce that there cannot be a learner, that the data gap has been taken care of. In that sense, you get non-learnability directly from heuristic hardness of the function. Because if you have heuristic hardness of the function, then suppose there exists a learner and your data is efficiently generatable. And suppose there exists a learner, that means that there exists a heuristic function for it, which you assume is not possible. That's sort of the argument that you do there.
What do you mean by heuristic here?
It's hard to evaluate on an epsilon fraction of inputs. And an epsilon is a part of the algorithm. So the algorithm is given. There does not exist an algorithm A which takes as input x and 1 over epsilon, which takes as input x and 1 over epsilon and is correct on an epsilon fraction of all possible inputs. That's what I mean by heuristic hardness. Okay, let us look at some examples, and this is perhaps the more famous one. Is the discrete logarithm problem of Liu, Temme, and Chernobyl-Sun, where they studied the following function. It takes as input some x, it takes the discrete logarithm of it, and checks if it's in a certain interval. And it looks like there's a discrete logarithm computation in it. So you think, well, a priori the data might not be efficiently generatable. There's something weird happening, right? Because if I give you x, you first have to do discrete logarithm and then check the interval. But there's a way to get around this. This function still has efficient data generation, and it's due to this pretty cool trick. If you see it, you see it, then it's not cool anymore. But if you don't see it yet, it's pretty cool. Instead of going from x to ci of x, what you can do is you can generate an x for which you already know ci of x. And how do you do this? You sample a y uniformly at random from 1 to p minus 1, and you compute a to the power y, where a is a generator of the group. So this is already sampling a uniformly random x for you, but now you know this example is of the form a to the power y. So you know y is a discrete logarithm. So you just check in which interval y is. Now it's not cool anymore with efficient data generation. Moreover, there's heuristic hardness. DLP is kind of cool in the sense that an algorithm that errs on a fraction of inputs can always return to an algorithm that never errs. And that's pretty cool. So what you do is you take an x, and suppose your algorithm errs on this x. But there are some other points on which it doesn't err. So what you can do is you can take this x and you can shift it. Shift it in a random way, and at some point you're going to end up in a region where it doesn't err. You compute the output there, and you simply just subtract the shift. So you take any algorithm which errs on, say, a fraction slightly larger than half, and then you can turn this algorithm into an algorithm that never errs by applying a shifting trick. Shift, try if it works. If it doesn't, reshift again until it works, and then you compute it, and then you subtract the shift. And you can actually check if it works because it's a checkable function. Which in complexity theoretical language means that if you assume that DLP is on P, you automatically get that the DLP is not in your heuristic. And we get a nice learning separation. But one thing that is slightly something that you might not like about it is probably relies on the hardness of evaluating the function. Like the ability to evaluate is pivotal in the proof. It means that in the proof you always write, okay, so now I have a learner, so now I can evaluate, which sort of contradicts the complexity theoretical assumption. And in some way, similar separations appear if I just consider a singleton concept class. So yes?
But the learner knows A or doesn't know A.
Yes, it knows A in the sense that it knows, yes, it knows A.
But so you
and it knows B.
The learner, you could just solve it.
Oh, Come again?
So you don't need to be a learner, you can just go.
It's exactly why it's strongly relies on evaluation, yes. The quantum learner just solves it, it doesn't learn it. Like one concept would be enough because it knows A, it knows P. There's indeed nothing happening, nothing learning happening. It's just, that's the criticism that I put in the bottom here. And we're trying to get rid of this sort of in the next few slides, where there's actually learning happening. This is exactly the observation that I was trying to make here. Because yeah, you can just consider the concept class, which is just one of these functions, let's say the 0th bit, let's say C0, and you get a similar learning separation, even though the quantum learner doesn't need any data. It's just a computation that the quantum learner does. And then classical learner also just needs to do a computation, but it cannot do it. Learning separation. This is really learning as opposed to computation. We can trivialize settings where you just don't need any data and we just have a singleton concept class. And sort of what intuitively one might think about as learning is this problem of identifying. So instead of having the evaluator function later on, I give you a concept class, I give you data, and you just have to point out which of the concepts is generating the data. I don't ask you to evaluate it later on, just point out which of the concepts is hidden in the data. Can we also, for this problem, establish separations where a classical learner cannot do it, but a quantum learner can? And another question that arises is, well, what about Feynman? What about his functions? What about his physics learning? These functions are not, like our magical formula for learning separation doesn't apply to these functions. There's no reason to believe that you can efficiently generate data for these functions, right? There's no reason to believe that. So you need a different formula. You need a different way of proving these learning separations because this efficient data generation giving rise to non-learnability directly from heuristic hardness doesn't work here. So we need different tools. And that's sort of the final part of this talk is sort of answering these two questions. But to answer one, we need to get slightly more formal. So what is learning separation? Let's be more formal here. Two places where quantum can come in. It's in the learning algorithm itself in the hypothesis class. So we get 4 categories of learning. CC problems are problems solvable with a classical learning algorithm and a classical hypothesis class. CQ, classical learning algorithm, quantum hypothesis class. So the first letter signifies the nature of the learning algorithm, and the second letter signifies the nature of the hypothesis class. We get some trivial relations between them. Every quantum algorithm, every classical algorithm can be efficiently simulated by a quantum algorithm. Let's not reverse that. And there is one slightly less one slightly less trivial relation in that the reverse of this inclusion also holds. And the reason behind that is that if your hypothesis is given the power of a quantum computer, any quantum learning that the learning algorithm needs to do can be offloaded onto it. In the sense that all the learning can already happen in the hypothesis class. That's sort of the intuition here. And these are equal. And it's just a lemma that I need to enable to say that, well, there's only 2 possible ways to separate classes here. It's actually 3, but we're talking about, since we talk about classical versus quantum, it is CC versus either QC, so quantum learning, classical hypothesis, or CC versus QQ, classical learners, classical hypothesis versus quantum learning, quantum hypothesis. You might also wonder about the separation between QC and QQ. There's also an example of this later on. It's not really studied in our paper.
What's the intuition for that level? Like
this one?
Like, I mean, you do have rigorous definitions beyond
Yes.
those lines, and then you
And then I
show
prove the lemma, yes. So what you can do is suppose I have a QQ problem, which is a quantum learning algorithm. And what I can do is I can define a quantum hypothesis class here, which is basically this hypothesis class prepended by the learning algorithm. So every hypothesis in this hypothesis class is the same hypothesis as this hypothesis class, but prepended with this learning algorithm.
Okay.
And then what I do is I just sample. I use my classical learner just to sample the oracle, just to gather my data, and then I just pick out the hypothesis which does the learning on that data and the evaluation of the hypothesis later on. It's offloading the learning basically. So the only thing that this classical learner does is sample examples. It's very trivial learning. It just samples, and it picks out based on these samples the hypothesis that this learner would do. Yeah, it just uploads the learning. That's the intuition.
So like if you fix the hypothesis class, then this doesn't hold. Right?
Exactly. Yes. You can namely also define somewhere where you can fix the hypothesis class. Indeed. Here, indeed, we are free to. In this proof, I have to adapt the hypothesis class. A very important point. Yes. But it also makes sense to fix the hypothesis class. One example of this is Hamiltonian learning, where you have a setup, you have some experiment, there's some Hamiltonian parameterized by some beta, and you just don't know beta. And you're given data, you can formalize this by having a hypothesis class given by functions corresponding to different Hamiltonians. Suppose in this, you could do Gibbs state stuff as well, but suppose now I here do expectation values of time evolutions of some starting state of this Hamiltonian, and I measure some observable on it. And if I now want to Bach learn this hypothesis, these hypothesis class, if I now do Bach learning, but I fix my hypothesis class to be this hypothesis class, it's basically the problem of identifying the correct beta. So I have some sort of data, which is basically evaluations of a function like this. And I want to find the beta which sort of best captures the data. And you get Hamiltonian learning. Whereas the simulation should be learning. And here, since we fix the hypothesis class, we only have one type of separation, namely the learning algorithm itself is quantum or classical. And here, indeed, you cannot offload because it's fixed, except if the function family is universal in the sense that it can do any BQP computation, and you can always offload, but this is a constrict restraint. So let's suppose your Hamiltonian family is constricted enough that you cannot compose arbitrary quantum computations inside. Okay, now we have definitions in place. Let's talk a bit more about intuition. So what is a learning task, and how do you, what kind of distinctions can you put on it? You can either talk about identification or evaluation, in the sense that I give you examples of a function and I want you to evaluate it later on, or I give you examples of a function and I want you to tell me which function it is. Just give me a classical description. I don't care if to evaluate it later on, just tell me what function it is. And the difference between these tasks is partly reflected in certain definitions I just put up. One being the difference between a CCQQ and a CCQC separation, where in a CCQQ, you need quantum to both identify but also evaluate later on. Whereas in a CCQC, you need quantum just to identify and to classically evaluate it later on. This is separation. And it's perhaps more strongly reflected in this fixed versus non-fixed hypothesis class. When fixed, you only need to identify which the hypothesis in my fixed hypothesis class is doing, not evaluate it later on. And what we ask ourselves in this first part is how close can we get to learning, which we just defined now as the problem of identifying from data. So I don't care about that the hardness must not lie in the function, in evaluating the function later on. It just must lie in the problem of identifying from data. So let's get towards that holy grail of learning. And we take one step closer, or people have taken one step closer. It's actually in reverse chronological order. This one was before the discrete logarithm problem. And this is the discrete cube root concept class, which is the concepts here are bits of the discrete cube root. What do I mean by the discrete cube root? I mean the inverse of raising something to the power 3, modulo n. So you raising it to the power 3, and the inverse is then called the cube root. And we consider the ith bit of it. Again, this has efficient data generation. Instead of computing the discrete cube root, you can just compute the power of something, and then of some number y, and then just as a label output the I bit of y. And this works because raising something to the power 3 is a bijection from Zn to Zn, Zn star to Zn. So sampling a y uniformly at random and then computing it to the power 3 is the same as sampling an x uniformly at random. It's a bijection. The push forward of the uniform distribution is the uniform distribution.
Is it a bijection for all n?
No, it's only a bijection if this is if n satisfies this. You're actually correct because you need an inverse. Yes. Free needs to have an inverse modulo Euler phi of 1. And we have n being two prime numbers, and this is the Euler phi. Like free needs to have multiplicative inverse modulo the order of the group, which is Euler phi of 1.
So we do have a proof, like we have a problem with that.
Yes, that's exactly with n is equal to. Yes, it's the promise. And this is basically saying free has multiplicative inverse in the Euler phi of n multiplicative group. Yes. I think it's an if and only if. But there might be weird. What is it? It's Legendre symbol, I guess you need to think about. And I think this is sufficient, but I don't know. It is at least sufficient. I know it exists for these n. Moreover, it's again random self-reducible. Similar tricks apply. But what is different between the discrete cube root and the discrete logarithm is that there is a backdoor. There is this magic d such that the inverse of raising something to the power 3 is equal to raising that same number to the power d. So the result of that number to the power d. In fact, that backdoor is computable by a quantum algorithm. So again, what we get now is not a CCQQ separation, but a CCQC separation, where the Q, this Q, basically what it does is it computes the backdoor, and then the C later on just does the modular exponentiation with respect to that D. So instead of QQ, CCQQ, we now have CCQC, where the Q computes the backdoor, and the C raises it to the power of that backdoor. Modular exponentiation is efficient. You can square and multiply. However, now the only thing that I need my Q for is again to compute the backdoor. This backdoor itself isn't hidden in the data. It's again a computational problem where I need my Q for. It again strongly relies on being able to evaluate. Q, you can again imagine singleton concept classes where I don't need any data. I just need to compute D, which I can do without data because N is known beforehand. Like the concept class is known beforehand. So again, no data is needed. So it's not super satisfactory. We're not there yet. This is why we came up with the modular exponentiation concept class. So instead of considering the discrete cube root, I'm now considering the discrete root, the discrete quartic root, and I don't know how to go to 5. But consider all of them. And my functions are nothing more than raising something to the power d. So intuitively, what the learning problem is now, I'm given examples x, x to the power d for various x, and I ask you what is d. And the important part here is that these concepts are efficiently evaluatable now. Like previously, the discrete logarithm, not efficiently evaluatable. Discrete cube root, not efficiently evaluatable. But these concepts are efficiently evaluatable. So hardness of learning these concepts can never come from having the hardness of evaluating them. Like a classical computer can simply evaluate them. The hardness must be in identifying which D is sort of hidden in my data. It is classical non-learnable because it contains the discrete cube root. Like I could generate examples for the discrete cube root, run the learning algorithm to solve that problem. So it's still not learnable. We have quantum learnability, in fact, which was the hard part to show. And it's actually kind of an interesting learning algorithm, I believe. Is that you're giving a bunch of examples, x and x to the power d. And your goal is to find d from this. And you're giving for various xi, let's say. But every example induces a certain congruence relation of d. Namely, we know that d has to be equivalent to L, which is the discrete log of x to the power d in the group generated by x, modulo the order of x. Like there's some periodicity with respect to the order. It turns out that the polynomial number of examples gives you sufficiently many congruences such that it is a full system of congruences. And if you have a full system of congruences, you can apply the Chinese remainder theorem to recover D from this. One caveat is that so far in the proof, we need to put one extra restriction on N for us to be able to show that the system of congruences is indeed full. But it is still plausible that these functions are hard that these integers still exhibit the DCR assumption, is that computing the discrete cube root is hard because they are widely used in RSA protocols, which is where the discrete cube root assumption comes from.
I mean, why do you say it's non-learnable? Like just because there's one instance where it doesn't work, does that really mean that it's classically not learnable?
Yes.
I thought you
Suppose-
for deltas and epsilons.
Yeah, but yes, there's deltas and epsilon, but there's also a for all C and C, which makes it non-learnable in this case. That makes any sense. We say it is learnable if for all concepts in the concept class it is learnable. So if there exists one concept in the concept class that is not learnable, then the whole concept class is not learnable, right? That's sort of the way we define it here. It is not, yeah, that's the way we define it. The concept class is only learnable if all concepts are learnable. And the epsilon delta comes in sort of the definition of what it means for what specific concept to be learnable. We could introduce, let's say, gamma parameter. I want to only be able to learn gamma fraction of all concepts, but this is a different framework. We say it's only learnable if all concepts are learnable. You could also maybe define, let's say, that's the average case for circuits. This is not an average case for circuits type statement. This is really all circuits, worst case for circuits. That's exactly what the difference here is. And the nice thing about this, we get CC/QC separation, but the hardness only relies on identifying. You need data to be able to find this D, and if you found the D, evaluation is simple. Like the classical hardness cannot come from the hardness of having to evaluate. It's really the hardness of finding the D's in the data.
Okay, I mean, I haven't thought about this too much, but like you're reducing it, like you're saying it's hard classically because of this discrete cube root
Yes.
Problem, which you've shown to be hard because of hardness of evaluation.
Yes.
Like there you have I mean, it's a bit weird that you say in the end that here the separation is not due to the evaluation, but the separation is because
Yeah.
it's a bit.
No, yes, I see what you mean, but I guess the point here is that being able to identify allows me to evaluate the different class of functions. That's sort of the point. So now suppose I can identify which D is in my data. Being able to identify will allow me to evaluate the discrete cube root. So it is still down the line on so many hardness of evaluation. It needs to be because it's about efficient learning and not, but now we don't say concepts are hard to evaluate, those learning separation. But now we get it's hard to identify because identification allows us to solve a problem that is hard to evaluation.
Yeah, it's super cool.
Yes.
The way it's related to the discrete cube root is by identifying the trapdoor.
Like this.
Like if you could turn the cube root in a way that's easy to evaluate, then the difficulty of the cube root will be a different one. And here what you're doing is kind of hiding the difficulty of computing the cube root into hiding the difficulty of finding the trapdoor function.
And you learn the trapdoor from data here instead of you have to compute the trapdoor without it. Still the crux. Yeah. So getting the trapdoor, you need to identify the trapdoor from data instead of computing it without any notion of data. Just there's a number.
Yeah.
The trapdoor and then.
Yes.
You see the codomain of this function is the integer multiple n, and it's an open question whether or not this is also possible for binary array concepts, which is more standard in these frameworks. Okay, final part. I'll have like 10 minutes, I think. I'll go through this. Okay, what about these quantum processes? What about Feynman? We have now done more identification. We've done some pedantic definitions and trying to capture this notion of identification, which is more of a fun thing. But what about actually useful separations in quantum processes? Again, clearly, it's not very plausible that you have efficient data generation here. So what else? What do we need to do? What do we need to do now to get learning separations for these problems without having to rely on efficient data generation? And the idea is that we just need harder concepts. Concepts need to be so hard that you cannot evaluate them even with data, which is, I guess, literally what I'm trying to say here. But what does this formally mean, let's say? So instead of saying the functions are just hard to evaluate on a fraction, they now need to be hard to evaluate on a fraction even when I'm giving data. And what does this sort of mean? I'm trying to answer now. Careful now that if I make my functions even harder, you still need to learn them quantumly, right? So don't make them too hard. That's sort of the balancing act here. And that's what we try to do. We try to map back learning onto complexity theory and see what we get. One simple step is every concept is a language. We're now doing binary value concept. So every binary value concept is a language in the sense that I say, I include my X in my language if my concept evaluates to 1. And every language is a concept by saying it's the identifier function. Let's say the function is 1 if X is an L.
Indicator.
Indicator function, thank you. That's exactly what I meant. So and vice versa. Okay, so what complexity class nicely captures efficiently learnable concepts? The learning algorithm is randomized, so we end up in a BPP regime. It can err on a fraction of input, so we end up in your BPP, heuristic BPP. No, it is not average BPP, because average BPP has to output don't know when it will be wrong. And in machine learning, you can just be wrong. There's no need to say don't know. You can just say this cat is a dog or this dog is a muffin. For these, there's of course part of machine. Let's say PAC learning doesn't care about being wrong. You can just be wrong. So we need to consider your BPP, not average. And moreover, we have this example oracle. And in a paper by Wang et al., Power of Data, the way they sort of captured this with complexity theory is what they call this sample oracle, this example oracle, which is a restricted form of advice. You could think about this for people who are in the know of complexity theory. We mix all these ingredients up, and what we get is what we call your BPP/SAM, which aims. So we give a definition for this. This is our complexity class, and which aims to one-to-one sort of capture the concepts that are efficiently learnable. Okay, so it's very nice to define your own complexity class. What else do we know about this? Yes.
But the distribution you mentioned in the beginning is then part.
Yes, that's exactly. In heuristic BPP, in these definitions, they don't consider languages. They consider what is called distributional problems, which is a tuple consisting of a language and a distribution. So something inside your BPP would be a tuple language, comma distribution. It's again not for all statements. For all distributions, it's sort of paired together. Right, so everybody can define their own complexity class, but let's now try to see if we can relate this to other complexity classes. And the nice thing about this is that, well, this sample oracle might be a bit weird. We don't know any problems that's sort of nice for this, or non-complete, whatever. However, what you get is that the sample oracle is upper bounded by polynomial advice terms. And what this basically means, as I already said, is that sampling oracle is a restricted form of advice. So what are advice clauses? These are languages that are solvable if I additionally tell you a bit string, a string of advice, that can depend on the language itself, on the problem itself, but not on the instance size. So we saw this a bit earlier. This backdoor would be a great notion of advice because it doesn't depend on the X, it only depends on my N. And if all of a sudden makes problem easier. So this is sort of why advice can help. You can have these backdoor in your advice string. And sample oracle is sort of a restricted form of advice. This is like the best possible advice that there is. Yeah. So this is yes.
But in these like advice complexity classes, the advice can be different for every like input, right? No, or is it like different, independent of the input?
Which one? The poly?
Yeah.
No, it is not. It has to be independent of the input. Just the instance size of the input. Okay. So for every instance size, there is a bit string.
Okay, I see. Which is the wrong way, I think.
Yeah.
Did I say it the wrong way? Oh, my bad. It's okay. It can only depend on the instance size, not on the instance.
Yeah.
And this is the truth. And whatever I said before this was wrong. Sorry. Okay.
I think you might. You're talking about the power of data paper here, right?
I am. Did I?
I'm just confused how it appeared in 2012.
2021. Oops.
It's
That would be very early. That would be impressive. Yes.
That was before he probably even started.
That's how Robert Wang writes so many papers as a time machine.
Okay. So what do we know? What do we need for non-learnability? We just need that my concept class contains one concept, right? So it's for all concepts. My concept class needs to contain one concept that corresponds to a language outside this URP/poly. So it's like an upper bound. It is actually sufficient to lie outside of this, but if you lie outside of this, you also lie outside of this. It's like a nice lower bound to what can be learned. Okay, we know that what is a different proof strategy. The solution we just came up with is we need concepts outside of this still kind of funky complexity class. And the whole point about the final part of the talk is let's unwrap the funkiness, like understand what makes this concept class funky. There's UR, there's poly, but let's relate this to more standard stuff and explain what the differences is between, let's say, standard complexity classes and this slightly more funky. But first, let's do one quick intermezzo. How do we get quantum learnability? Like, these concepts are hard, but are they still easy enough for quantum? And we use a boring trick. What we do is we additionally constrain our concepts to lie in BQP. So there is a way to evaluate them, and let's suppose there are just not so many of them. If there's not that many, you can brute force fit to the data, and the idea of empirical risk minimization will tell you this will be your concept that is with 1 minus delta probability epsilon correct on the rest of the data. So for quantum learnability, we cheat a bit, and a nice thing, let's see, can we get examples, so these future research, can we get examples where quantum learnability doesn't come from cheating? Can we find exponentially sized concept classes that are quantum learnable but not classically learnable? Which in our case only gives you polynomially sized because we need to be able to brute force. Okay, let's unpack the funkiness of URP/poly. DOP is an example of this, which is nice. In fact, it is so nice that if we are given just one example that exhibits this, then it turns out that every BQP complete problem exhibits this. In the sense that if there exists one L, which on some distribution D lies outside of URP/poly, but it lies inside BQP, then every BQP complete problem, there exists a distribution for which it also lies out of heuristic P/poly. And the trick is you just consider the push forward distribution of the reduction. It's BQP complete, so there exists a reduction from the language L to L prime. And now if you define your distribution D to be the push forward, D prime to be the push forward of D under the reduction, then being able to solve this problem in URP/poly will allow you to solve this problem in URP/poly, which we assumed is impossible. So, however, note that the way you get the distribution now is artificial. If you, for instance, use the DOP for this, you again encoding DOP in your learning problem, now not from the language side, but from the distribution side. We're sort of hiding the DOP now not in the language. We're still talking about the BQP complete function. For instance, Hamiltonian simulation, matrix inversion, wherever your favorite quantum problem is. But the heuristic hardness still comes from DOP through the distribution. Like you're saying, oh, Hamiltonian simulation gives a learning separation, but still using DOP in the distribution. Okay. However, how do we get one such problem? We said one such problem is enough for all of them. How do we get one such problem? And it actually kind of already looks like something which is more natural in the community is the assumption that BQP does not lie inside P/poly. And the intuition behind this is that we know that BPP lies in P/poly because we can capture classical randomness using an advice frame. But we're saying, well, quantum randomness is actually quite different. It's something that you cannot sort of summarize in one advice frame, sort of inherent in this quantum thing. There's no classical way of extracting all the quantum randomness from your problem and writing down an advice frame for it. And moreover, if the assumption were not to hold, this would break many cryptography protocols. Okay, but how far is this assumption from this? And the answer is, well, you just need you just need a random self-reducibility of the problem. Such that if we have a problem outside of P/poly, and it is also random self-reducibility, then you can put heuristics there.
Sorry, what's random self-reducibility?
That's exactly the statement that an algorithm that errs on a fraction of input can be turned into an algorithm that never errs. but then given like a nice definition from Fortnow in 90s.
And the random here.
Is this shifting? The shifting is a random protocol, for instance.
Okay.
And sort of you're saying, if my algorithm is correct on an epsilon fraction with respect to this distribution, then I can turn it into an algorithm that never errs by playing around with this distribution.
Okay.
It's just a randomness. You have to hope that you at some point end up in the correct part of the space, the part of the space where your algorithm is correct. So you're randomly applying shifts, hoping that you finally end up with that. That's the random self-reducibility property. And yeah, so random self-reducible with respect to D will give you this this property. Which basically you can tack on the heuristics here. Okay. Now let's put all these lemmas into one corollary. We see that one single problem is enough for all BQP complete problems to be such that it exhibits the learning separations. You might get artificial distributions. You will get them actually. To find such a problem, we need one in BQP that is also random self-reducible outside of Peirce's poly, which now if we want to summarize this in one corollary, all these lemmas, we get that if there is a language in BQP that is outside Peirce's poly and it is random self-reducible, then every BQP complete problem gives rise to a CCQQ separation. Of course, we know that this holds for DOP. So in fact, what this corollary shows is that every BQP complete problem can be reformulated as a CCQQ separation. Well, on the surface, it might look like your favorite BQP complete problem, say Hamiltonian simulation. It's still underlying it, we'll have in the distribution discrete logarithm. So indeed, with an artificial, perhaps, distribution. So for instance, as I said, you could take Hamiltonian simulation, and I could now construct a distribution over inputs where I'm using a DOP such that this induces a CCQQ separation. Would of course be nice, at least that's what we're thinking about now, is how do we get rid of this DOP assumption? Are there more inherently quantum problems that have this random self-reducibility property? Random self-reducibility typically comes from some sort of algebraic structure. It has been studied, for instance, for matrix inversion. I'm looking into that as well. But we're trying to sort of find BQP complete problems that have this sort of random self-reducibility problem from some algebraic structure. If you want to discuss this later, I'm happy to do so. There's some stuff I'm thinking about now. Where do we get this random self-reducibility problem? Yes.
So basically, this is kind of proving this like folklore statement that you can hide discrete logarithm anywhere if you want and make a learning problem.
Yeah, and you can. Every BQP complete problem exhibits a learning separation, and you can use DOP for this.
No.
But you can basically use any problem which quacks like DOP.
Okay.
And what does quacking like DOP mean? That's sort of the two lemmas we looked at. Okay, to wrap it up, time. What is the learning separation? Various definitions, various different tasks, identification versus evaluation. Existing stuff uses the fact that it's sufficiently generatable, however, strongly relies on evaluation. We extend to identification. Identification being the hard part, which gives rise to evaluation. What about quantum processes? There's no reason to believe you get efficient data generation, so you must make them even harder. How hard must you make them? You must make them outside your Peirce's poly hard. And if you don't consider too many of them, you can also get quantum learnability, and you can use the discrete logarithm again, or problems that quite like a discrete logarithm, to build learning separations from any BQP complete problem. And you can use problems that quack like a duck, which is basically saying this, and it's now trying to find one so it exhibits this, what we are thinking about. Well, thank you very much.
Great. Thank you, Casper. This is very nice. I think we're still doing okay in time. If anyone has questions, they say no time pressure. Ask the question to your heart's content.
Renaud?
Nobody else wants to. Could you repeat your argument about saying that classical advice can't simulate quantum randomness?
Cannot, is the idea.
Yeah, but because I mean, if you measure, you just get around this thing. So why? What is the argument again?
I don't know, I just read a blog by Scott Aronson who said this. Okay, let's do the obvious thing is let's try to apply the proof that BPP is that which Adam wants proof, which says that BPP is contained in PSX poly. And what the proof does is in a BPP algorithm there's coin flips, right? And every time there's a coin flip, and by doing not one coin flip procedure that you would do in BPP, but like 18 of them, and then taking the majority vote of the outputs, you get one sequence of coin flips that works for all x. So normally for every x there is a sequence of coin flips. You turn that statement into there exists a coin flip sequence that works for all x. But in quantum, you don't have these sort of coin flips that happen. What would these coin flips be? There's like, how would you extract these coin flips from your quantum circuit? I would sort of, my question would be.
The argument is more that the whole proof doesn't work.
That's my argument. There might be people who are smarter than me that have better arguments. But this is,
I never really heard that argument.
That's a good. Yeah, that you cannot extract the classical.
I mean, like the statement of the complexity class being different seems like a valid conjecture, but are you informed somehow quantum randomness being fundamentally different than classical?
I don't know if that's actually, yeah, more like a reformulation of what the statement looks like, right? Like this whole statement that BQP is not contained in PSX poly is verbatim. You cannot extract quantum randomness in an advice frame. That's like one-to-one, basically the same statement.
I mean, BQP is also larger than
Sorry?
BQP is also larger than there's two components.
Fair, as you also know. It's not verbatim, you're right. It's like, okay, no, yeah. Yeah, I don't know much more than Adam doesn't work.
Yeah, thanks.
So at some point in the last section of the talk, you had somehow identified like the intersection where these like hard enough concepts to get a separation lie, and then you went down this path of like showing that if you find something in BQP and then there's some BQP complete problem, then okay, that's interesting, but I would like to go back to this point where you find that kind of this kind of sweet spot.
Yes.
Are there any ideas, or do you have any ideas of how like to go about identifying natural problems in here, like concepts in here where you don't need to have this issue of like again having the distribution being this artificial?
Yeah.
I guess I'm asking like it's a big question, but like do you have any ideas of how to tackle this?
Yeah, so finding BQP complete problems that are random self-reducible.
Yes.
That would be the answer to this, unfortunately. There are candidates sort of for this that we are considering. One would be this large body of sort of random self-reducibility matrix inversion, which is a quantum, I don't know, but it is interesting. Other ones would be like, for instance, there's like signal processing stuff has a lot of algebraic structure. Maybe because it has like some parameters, and maybe you can extrapolate between the parameters. That's something that I'm thinking about.
So what's actually the status here? Is it we have lots of BQP complete problems and know that they're not random self-reducible, or we have lots of BQP complete problems and we just don't know whether they are?
That's what we studied before.
Okay, so you don't have to find a new BQP complete problem, but you study the ones we already have.
Yeah, it hasn't been studied, let's say, necessarily. No reason for it. That was.
But what would be the way of showing that? Like,
what would be the way of showing that?
Does it seem like something you could show for like big problem?
That's actually, I don't. How do you?
Like, the question was that it's possible to do.
No, I think it is possible.
Yeah, like as a researcher, not.
If they exist, do they exist is then also the question, right? And that's sort of how I want to answer, because all these things that we do know random sort of reducibility of, they have like a very strong algebraic structure. So this discrete cube root goes over integers modulo n. There's like a very sort of algebraic structure on the instance sizes, let's say. There's like bijections, net multiplication, inverses, all this stuff is nice. And on quantum, it's not as clear if there's the same structure on certain problems. So you would have to find a BQP complete problem with this nice algebraic structure, which they exist, and then you would have to check if they exist, if it sort of is enough structure for random self-reducibility. Do I believe they exist? I don't know. I don't yet believe they don't exist. But yeah, I don't yet believe they don't exist.
Maybe like do I get it correct? And that even if you like assuming they exist, assuming you can find such an instant, the problem that you would again have, for which you would have the separation, it would be like a highly kind of, you know, it would rely on some algebraic kind of structure underneath.
Yes.
That you seem to be convinced that it's like necessary.
It would be very surprising to me if you would get random self-reducibility from something else than an algebraic structure. Maybe I'm not as knowledgeable about physical systems, or maybe some interpolation between parameters in a parameter space might happen. But I can get correct answers on a fraction of certain configurations of your system, which allow me to fit a function through it entirely. I don't have the physical intuition. Like it's I'm more of an application. I need to have algebraic structure to feel comfortable to think about this stuff. But there might also be for physical instances, but I just don't know.
When you say you want it to be like random self-reducible and BQP complete, is this a very strong statement about just like that everything in BQP would then have this property in a certain sense? Because you can.
It need not be BQP complete. It just needs to be in BQP.
Ah, okay. Oh, sorry, I got that wrong. Okay.
If it is just then, so how you would get the BQP complete one is again to use the random self-reducibility of the BQP one and push forward the distribution.
Yeah, okay.
But that's for other BQP complete. So then again, the one is enough for all. So it would apply, but with let's say a more quantum distribution, because it is the random self-reducibility structure of a quantum problem, not of the DOP. Yes.
So do you look into all this like in subgroup stuff, like where you have a group structure and all these things?
I mean, it's that BQP complete.
I don't know.
I don't know many
But there's a group
instances of this that are. Sorry, no, yes, you could. For DOP, it is a subgroup problem, right? That's sort of the. You could get this for in subgroup instances. For the general one, I don't know what the conditions on your groups needs to be for this to be peak. It would be nice actually. And you could go beyond the DOP by having more general groups. That is actually a nice way of getting there.
And there a paper precisely about like going beyond DLP but staying in cyclic groups, which is like the
Is this by one?
no.
No, yeah, I know there are groups beyond the DOP that I have an efficient quantum algorithm for the inner subgroup problem.
I mean, you need fast forwarding, I guess.
That's one way of thinking about it. Also, need some, I don't know, abelian Greenhoff. I don't know if that's fast forwarding. That's sufficient but unnecessary, I guess.
Quantum complexity for discrete logarithms and related problems by Han, Yamakawa, and Yu.
No, but it would be nice to think about conditions on a group that would give rise to random self-reducibility. Like what makes it work, or then again, it's the same here, like what makes it work for the DOP, and then you look at the conditions on the group, such that the hidden subgroup problem of that group is random self-reducible.
And you could also try to just like add more algebra to it, right? If you say, I also now allow for multiplications,
Yeah.
give more structural thing, hope that it's still solvable in this kind of thing. But yeah. I have another question. You said it like you only have polynomially many concepts or something like this at some point.
Yes.
I mean, not completely getting everything, but if you only have polynomially many, could you not just like somehow for this specific set of polynomially many problems come up with some polynomial size advice that you can give a classical algorithm to better solve the problem or something like this? I mean, very
Well, if it lies outside European/poly, then there's no advice that works. So this is why this sort of
Okay.
requirement is necessary.
Yeah.
Which is basically saying there is no advice that makes it work. If BQP can be problems, it is safe to assume that no advice works, but you just need random subgroups.
Awesome. Any other questions? Others, we said Casper will disappear soon, but not now. So you can still join up on him recording.
Maybe last question, like you mentioned it a few times that, oh, maybe then we get a bit like a more natural distribution, right? Because it comes from quantum, like why? Why is this a more natural distribution necessarily?
Yeah, it's not the DOB, I guess. That's that's a very good question. Indeed, because you're doing push forwards, then afterwards, and then you get it's again getting scrambled up. Yeah, would I personally be more happy if my Hamiltonian simulation is hard on a different distribution except on the instances of discrete logarithm? I think I would, but I don't know how much I would. Like I wouldn't say, oh, Hamiltonian simulation is a hard learning problem because now the distribution. I guess there might be distribution which is more satisfactory, but just not in the OP might not be sufficient.
Wouldn't it be better if you actually had a learning problem that would be difficult to learn rather than kind of a computational one? Like something that more naturally feels like learning.
That's a very more naturally feels like learning.
I mean, you have the same when people talk about optimization problems and they encode DLP. It just feels wrong because it's not an optimization problem of some form. But it's also not really a learning problem.
What would be a learning problem for you?
Hamiltonian learning would be a learning.
What if I give you the problem of I give you time evolved expectation values of a time evolved state under a Hamiltonian? You tell me which Hamiltonian is giving a time evolution. So
Yeah.
to this, for instance.
This feels more natural.
This is but this is not hard. I can show you it's a learning separation, but there's still DOP happening inside in the distribution.
Yeah.
But it is what you would still call as learning problem in your dictionary, you know?
Yes, but not the distribution. Right?
Yeah, not the distribution,
You
yes.
want something where both
But you need a distribution that comes from a learning problem. That's like what does that mean?
like smooth,
Like smooth.
not weirdly peaked.
Yeah, that works. That's a nice one. Yeah, actually, that's maybe a more natural condition.
But is there a single distribution where one would really be happy to?
Yeah, that's also a very good question.
At least you want like a broad class, right?
For most distributions type stuff.
Yeah.
Yeah.
To like convince a practitioner.
Yeah.
Like this imaginary practitioner that we always have in our mind.
Yeah. Meet him someday.
But I mean, in the end, if you want to show some computational complexity, you better link to some computationally hard problem, and either you hide it under the carpet and say, I'm so naturally learning, and under the rug you're still just encoding DLP or whatever it is that you encode, or whether you're just honest and say, well, that's what I encode, take it or leave it. I think it's more a matter of taste than of place. What's more natural or right?
I mean, we don't know of a single natural quantum optimization problem that optimization problem that a quantum computer can solve in a classical one time. Yeah, like that's something that
I don't even know what that means. A single natural quantum optimization problem.
something which is not DLP.
That's okay. Fair.
Function.
I don't know. Well, yeah. UP is kind of quantum. I don't know. But UP is kind of quantum. Like the hidden subgroup problem is kind of quantum. It works on a quantum.
What do you mean by a natural quantum optimization?
Yeah, exactly. That's my point. And then you're obviously not
Of natural quantum optimization problems, like I mean, ground state finding, like finding the lowest energy of a system, trying to some naturally defined generic quantum circuits and trying to optimize them.
I can give you a system. It's a guitar from Antonio for DOP.
But sorry, question, because I'm a bit of an outsider to all of this. Isn't that not the point of complexity theory learning separations, to come up with natural things? Isn't it precisely to find a smart mathy thing which allows you to make the big statements, that worst case, and then you go home?
Yes, you also have assumptions, right? If you just assume quantum computers have a learning capability to classical, you would be done. And now you're reducing it to other assumptions that are more justifiable. So trying to justify those, arguing that they make sense, is still process.
Yeah, no, like I wasn't bashing on you. I was just asking, like, from the mindset perspective, would that still fit this whole? But I'm asking because I don't know.
Also, I think that like the problem is because you deal with computational complexity. Like if you would say learning in the sense of information theoretic complexity, then well, there are other more natural problems that give the separations, like essentially all the way to by a robot.
Yeah. But then you have an org.
Yeah, I mean that's where the information comes from, right?
Okay, this is super good. Nothing else to say. Is there something that's
Also from my side.
Hi, Jens? Yeah,
No, so the sound was terrible, but I could hear very well.
very good. Thanks for the recording. We'll make this available on Slack.